Hello all. Coordinate system. Introduction. In description of motion, one has to first devise a method of how to describe the space. In other words, we must have a mathematical procedure that uniquely specifies the position of any point in space. The mathematical system which uniquely determines the position of any point in space is called coordinate system. The method essentially consists of simple geometrical shapes which may fill all of space. We find simple method of describing the shapes first and then extend our ideas to describe entire space. We shall discuss three coordinate systems, namely rectangular coordinate system, spherical polar coordinate system and cylindrical coordinate system. In rectangular coordinate system, straight lines are the model shapes. In spherical polar coordinate system, spheres are the model shape. And in cylindrical coordinate system, cylinders are the model shape to describe space. Rectangular coordinate systems. The straight line. Consider a straight horizontal line. Any point on a straight line can be uniquely identified by its distance from some fixed reference point called origin and its direction from the origin. For example, point P on the line is at a distance of 7 units on the right of the origin O. We describe the position of any point P by the movement along the straight line that leads directly to the point P from the origin. How far we have to travel to reach the point P from the origin O is given by the length of the straight line segment drawn from the origin to the point P. Moreover, one must also specify the direction of the point P relative to the origin O. Thus, the position of a point is given uniquely by the distance x and the direction from the origin O. The position of an origin relative to itself is thus given by x equal to 0, because to go to the origin from the origin itself, the line extending from the origin to origin itself has 0 length, and therefore the position of origin relative to itself is represented by the number 0. The movement along straight line from one point to the other represented by the length of the straight line together with the direction of movement is called displacement. So, in the diagram, blue arrow represents displacement. The length of the arrow is the magnitude of displacement that represents how far we have moved, and the direction of the arrow is the direction of movement. Let x1 be the displacement towards right and x2 be the displacement towards left, such that when they happen one after the other, we come back where we started. The net displacement is therefore 0 because we have come back where we started. So, no displacement, initial and final position, they both coincide. Net displacement 0 can be expressed as the sum of the two displacements in opposite direction, x1 plus x2 equal to 0. We represent displacement towards right by positive numbers, while the displacement towards left will be represented by the negative numbers, because the two opposite displacement when happen one after the other produces 0 displacement if their magnitudes are equal. So, the displacement in the opposite direction must be represented by the positive and negative numbers, because when they add we get 0. Thus, points on a straight line are identified uniquely in terms of displacements leading to them from the origin on the same line. When a horizontal line is shifted vertically parallel to itself, it traces out a plane. Having learned how to represent points on straight line, we now proceed to learn how points on the plane can be uniquely identified. We label the points on the straight line as shown. Now consider the point P on the plane as shown. We start from the origin and travel horizontally and then vertically to reach the point P. We travel 6 units in the horizontal direction and 2 units vertically upward. These two displacements uniquely determine the position of a point P relative to the origin O. We represent the position of a point P by an order or pair 6 2, in which the first number represents the horizontal displacement and the second number represents the vertical displacement. The order or pair is called the coordinates of a point P. The vertical displacements are measured from the horizontal line highlighted. This line is called the x-axis. The vertical line through the origin is called y-axis. The plane form is called xy plane. X-axis and y-axis forms a plane which we can see on the screen. In general, starting from the origin, if x is the horizontal displacement and y is the vertical displacement, then the point reached has the coordinates xy. The first number is called x coordinate, while the second number is called y coordinate of a point. If we choose to travel first in y direction and then in x direction with the same displacements y and x respectively, we again reach the same point P. That is, the coordinates of a point are independent of order of displacements. To go to any point on x-axis from the origin, we don't have to travel in y direction. That is, the y coordinate of all the points on x-axis is 0. Therefore, the x-axis is represented by the equation y equal to 0. Similarly, the equation of y-axis is given by x equal to 0. Because when we have to go to any point on the y-axis, we only have to move along y-axis. We do not have to move horizontally or in the direction of x-axis. So, no displacement in the direction of x-axis. This means that the points on the y-axis have only y coordinate and 0 x coordinate. The x coordinate and the y coordinates are also called abscissa and ordinate respectively. Describing space. We started with a straight line. Shifting the straight line parallel to itself traced out a plane. When a plane is shifted parallel to itself in a direction other than that lying in the plane itself, it fills all of space. And now we have a model that fills all of space. And now we can understand how we can describe every point in space relative to a fixed reference point called origin. Suppose that the origin is present on this plane. We have now understood already how to uniquely identify the points on plane. Now we extend our ideas to specify the position of points anywhere in space uniquely. Now suppose the point P present anywhere in space, that is outside the planes that is shown. We shift the plane in a direction perpendicular to the plane and arrive at the point P. This suggests that the point P can be reached from the origin by undergoing the displacement in x direction, displacement y in y direction and the displacement z in z direction perpendicular to the plane. The position of a point P is now uniquely represented by these three displacements. The position of a point is represented by the order triplets x, y, z called the coordinates of a point P. The first number x is the displacement in x direction, the second number y is the displacement in y direction and the third number z is the displacement in z direction. The third direction is labeled as the z direction. Again, it is not necessary to first travel in the x direction, then in y and then in z direction. We may choose to travel in these three directions in any order. Eventually, we will reach the same point. The condition is that we must travel the same distances in the respective direction. We must always travel the distance x in the x direction, y in the y direction and distance z in the z direction. Whichever the order of displacement we choose, we eventually reach the same point. Consider the line in the z direction passing through the origin. Starting from the origin, to go to any point on this line, one has to travel only along the same line. So, by red line we have shown a line that passes through the origin. From the origin, if you want to go to any point on this red line, we have to only travel along that red line only. We do not have to travel in x or y direction. This means that the x and y coordinates of the points on the red line are 0. Therefore, x and y coordinates of all the points on this line are both 0. This line is called the z-axis. If the point is present on the xy plane, its z coordinate will be 0 as no displacement in z direction is needed. The xy plane is the plane formed by x axis and y axis. We know that the two lines intersecting at a point determine one and only one plane. So, plane determined by the x axis and y axis is called xy plane. The equation of xy plane is given by the equation z equal to 0 because in xy plane all the points have 0 z coordinates as we do not have to move in the z direction to go to any point on the xy plane from the origin. Similarly, we have yz plane and xz plane described by the respective equation x equal to 0 and y equal to 0. YZ plane is this vertical plane that passes through y axis and z axis. From the origin to go to any point on this YZ plane, we do not have to move in the x direction. So, x is 0, x coordinate is 0 for all the points on YZ plane. Therefore, we say that x equal to 0 represent the equation of YZ plane. Similarly, the XZ plane, the horizontal plane that passes through x axis and y axis. For this XZ plane, we do not have to move in the y direction, we only move in the x and z direction to reach any point on this xy plane starting from the origin. So, no movement is required along y direction, so y coordinate will be 0 for all the points on xz plane. So, we say that y equal to 0 represent the equation of xz plane. Cartesian coordinate system. We now briefly outline how the coordinates of a point are determined. This is x axis, this is y axis and this is z axis, and the origin is O, which is the common point of all these three x, y, z axis. All these x, y, z axis are perpendicular to each other. P is any point. Now, how to specify the coordinates of the point P using the coordinate system we have just discussed. We start from the origin and let us first travel in the x direction. We travel the distance of x in the x direction, distance y in y direction and then distance z in z direction to finally reach the point P. Then the coordinates of the point P will be x, y, z. This method of determining the position of any point in space is called Cartesian coordinate system in the honor of its inventor Rene Descartes. Polar coordinate systems using angular quantities. The angular coordinate. When a particle moves on a circumference of a circle, the motion can be described in a simpler way by using an angular coordinate. An angle made by the radius vector with the fixed line called axis represents the position of a point on a circle. This is the reference axis from which the angles are measured. It is called axis. An angle theta represents the angular position of a particle. An angle made by the radius vector. The radius vector is an arrow that extends from origin, which is at the center of the circle, to the particle which is moving on the circumference. So, angle made by the radius vector with the axis represent the position of a particle. Obviously, this angle theta will be between 0 and 2 pi when the circle is traced in anticlockwise direction. The angles measured in anticlockwise direction from the axis are positive, and the angles measured in a clockwise sense are taken as negative, because when we consider two angular displacements of equal magnitude but in opposite direction, the net angular displacement is 0, the net angle trace is 0. So, two angular displacement in opposite direction add to give 0. So, they must be represented by the negative numbers. The plane polar coordinates. The circle expanding along its radius traces out a plane. The diagram shows the circle position at various instances of expansion. The circles are concentric with the center O. So, now circle is the model to describe the plane. In the previous coordinate system, the Cartesian coordinate system, we pulled a straight line parallel to itself and it formed a plane. So, that was the model for the plane in the previous case. In the present case, an expanding circle which traces out a plane will be a model for describing the plane, for describing the position of every point in the plane in a unique manner. The position of any point P in the plane may be represented uniquely in two steps. First, find the circle on which it is present. Then specify the angular position from the axis. So, this is how we uniquely specify the position of any point in plane. First, we specify the circle on which it is present, and then the angular displacement of radius vector. We take the origin of our system, coordinate system, at the center of all these concentric circles. Thus, the position of any point in the plane can be uniquely represented by its distance r from the origin, which is simply the radius of the circle upon which the point is present, and an angle phi. This system is known as plane polar coordinate system, and r and phi are called polar coordinates. Spherical polar coordinates. What if the point is present outside the plane? An expanding sphere fills entire space. The diagram shows position of sphere surfaces at various moments during expansion. They are concentric sphere. So, sphere is a model for describing entire space. A growing sphere or expanding sphere fills all of space. So, this idea will enable us to represent the position of points anywhere in space in a unique manner. If one could find how to determine the position of a point on a spherical surface, then the position of any point in space can be uniquely determined using the following procedure. First, find the sphere on which the point is present. This gives us the distance of the point from the center, and we take center as the origin of our coordinate system. Then determine the position of the point on that sphere. We now proceed to find the method of determining the position of a point on spherical surface. Suppose that concentric circles with the center at O form the horizontal plane. We draw horizontal and vertical axis through the center O. Consider the circle of radius r. Now consider the semicircle of radius r in the plane of horizontal and vertical axis with the same center O. So, this is a vertical circle. The concentric circles form horizontal plane, and this is another vertical circle with the same center O. When this semicircle is rotated about vertical axis, it traces out sphere in one complete rotation. We have shown only a partial rotation here, but if it is rotated in one complete revolution, it will trace out a spherical surface. This is the horizontal circle or an equatorial circle for the sphere that is formed by these vertical circles. Equatorial circle means the circle around the sphere which is at the same distance from the top point and bottom point of the sphere. The position of a point on the sphere or spherical surface of radius r is determined as follows. Consider the point P as shown. First find the vertical circle on which the point is present. Vertical circle, which is one of the many vertical circles which form the spherical surface. The position of the vertical circle is given by the angle phi made by the radius vector in the equatorial plane with the horizontal axis. So, we first found the vertical circle and then the position of vertical circle is given by the angle phi. Now, the position of the point P on the semicircle is given by the angle theta made by its position vector with the vertical axis from upward direction. So, these two angles theta and phi uniquely specify the position of point P on a sphere of particular radius. The angle is made from positive y axis or from the upward direction, and this angle is only between 0 and pi, because the maximum value of the angle theta will be pi when the arrow blue is rotated towards the downward direction of vertical line. Thus, a pair of coordinates theta phi uniquely determine the position of a point on a given sphere of radius r. So, now we have a method of determining the position of a point on a particular sphere of radius r. The two coordinates theta and phi determine uniquely the position of a point on a spherical surface. The position of a point present anywhere in space can be determined by the following three steps. First, find the sphere on which it is present. The sphere has the radius r, which is also the distance of the point from the origin. Now, the position of a point P on this sphere is given by the pair of angles theta and phi. The position of any point in space is thus uniquely determined by the triplet of coordinates r, theta and phi. The distance r from the origin is called radial distance, the angle phi is called azimuthal angle and angle theta is called polar angle. The triplet r, theta, phi is called spherical polar coordinates and the coordinate system is called spherical polar coordinate system. Relationship between spherical polar coordinates and Cartesian coordinates. Look at this diagram. We have shown both Cartesian coordinates and spherical polar coordinates in the diagram. Let the vertical axis be the z axis and the azimuthal angle phi be measured from x axis of the Cartesian coordinate system. In triangle OPQ, OQ is equal to OP sin theta, which is equal to r sin theta. OP is the distance of point P from O. In triangle OQR, OR is OQ cos phi and OQ is already r sin theta, so we have r sin theta cos phi. And OR is just the x Cartesian coordinate of a point, so x is equal to r sin theta cos phi. This equation relates spherical polar coordinates r, theta, phi with the x coordinate of Cartesian system. And QR in the same triangle is OQ sin phi, which is equal to r sin theta sin phi. QR is y coordinate So y is equal to r sin theta sin phi. This is another equation which relate y coordinate of Cartesian system with spherical polar coordinates. And in triangle OPQ, PQ equal OP cos theta equal r cos theta, and PQ is the z coordinate. So z is equal to r cos theta. Cylindrical coordinate system. Cylindrical coordinates. A cylindrical surface is formed by the vertical lines all at a fixed distances from the axis. The position of any point on the cylindrical surface is specified by the vertical line on which the point is present and the distance of the point from certain point on the line. We have already devised a method of specifying the position of point P on a straight line in discussion of Cartesian system. The cylinder growing in size fills all of space. The diagram shows the cylindrical surfaces at various moments during expansion. They are coaxial cylindrical surface. Expanding cylinder fills all of space. So cylindrical shape is now our model to describe entire space, to describe the position of points in space uniquely. Consider any point P on one of the cylinders of radius rho. Consider the circle in horizontal plane with the center on the axis and having the same radius as the cylindrical surface. The point P is present on vertical line L along the cylinder surface. The position of the line L is given by an angle theta as shown. And the position of a point P on the line L is given by the distance z along the vertical line from the horizontal circle plane. Thus, the position of a point on a given cylindrical surface is uniquely determined by the coordinates rho, theta, z. Relationship between cylindrical coordinates and Cartesian coordinates. In the diagram we have shown Cartesian coordinates x, y, z and cylindrical coordinates theta, rho and z, they will be shown. Let the vertical axis be the z axis and the azimuthal angle theta be measured from the x axis of the Cartesian system. In triangle ORQ, the angle R is 90 degree and therefore OR equal OQ cos theta. OQ is diagonal and OQ is simply the rho, the distance from the z axis, which is a cylindrical coordinate, rho sin theta. So x is equal to rho cos theta, OR is x. So this equation relates the cylindrical coordinate rho theta with the Cartesian coordinate x. Similarly, RQ equal OQ sin theta equal rho sin theta, and RQ is y coordinate of Cartesian coordinate. So y equal rho sin theta is another equation relating cylindrical coordinate rho and theta with the y coordinate of Cartesian system. And z coordinate is the same in both the coordinate system, which is simply the distance of the point along z direction from the xy plane. Thank you.